Okay, we're going to take a running start at this. We already did this problem. So we know if you have the molar mass, grams per mole of an element, you can go back and forth between moles and mass and moles. And then we talked about compounds, and I think I'm just going to go through this last problem. We said the molar mass for a compound is the molecular weight or the formula weight, which is in AMUs, but then you just change the units to be grams per mole. So for instance, in this case, we're going from moles of methane to grams of methane. So we need the molar mass for methane, which that's almost about as fun as saying the molar mass of magnesium. So we said that if you have a periodic table, you can take 1 plus the decimal number for carbon, 12.01, plus 4 times the decimal number for hydrogen, 1.008. And you get a molar mass of 16.04 grams per mole. And then we can work this problem. We'll start with the moles, 0.444 moles, 0.4444 moles. And you could put CH4 if you wanted to, but since there's only one compound, it's optional. And then use the molar mass, grams per mole, so units of moles cancel, we're left with units of grams. Rounded to 4 significant figures, we get 7.129 grams of methane, okay? All right. So can you see where, now this is a new problem. This problem is a little different. It looks similar to the previous problem, but the title says we're going from mass, grams, to moles of atoms, not moles of the compound. And remember, the thing in brackets may not necessarily be there in the same problem. So it could say how many moles of bromine atoms, it's the same thing, are there in 1.92 grams. Do you guys have this one? Okay. Are there in 1.92 grams of carbon tetrabromide? So, kind of thinking through this then, given the formula C1Br4 for a repeating unit of CBr4, do you buy this that we have 4 bromine atoms and 1 carbon atom in 1 molecule of CBr4? Now I added something today. Well, let's scale it up. Instead of just 1 atom, let's have a dozen atoms. Let's have 12 CBr4 atoms. Do you buy this? If we chop up those, molecules. Let's have a dozen CBr4 molecules. Molecules CBr4. And let's chop it up into piles of carbon and piles of bromine. Do you see where we're going to have a dozen bromine atoms? Oh, did I do 4 dozen bromine atoms and 1 dozen carbon atoms? I totally butchered that. I guess adding it. All I'm saying is that if you have, there's my carbon, bromine, 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 bromine. If you have a dozen of those and you chop them up, then you're going to have a dozen carbon and 4 dozen bromine. Well, the concept of a dozen is the same thing as a concept of a mole, except instead of 12, you have 6.022 times 10 to the 23rd. So if you have 1 mole of CBr4 molecules, and you chop them up and make your piles, 2 piles, 1 pile of carbon, 1 pile of bromine, you are going to have 1 mole of carbon atoms and 4 moles of bromine atoms. Okay, so you're basically dissecting a CBr4 molecule. Well, that actually then leads us to this relationship with regard to moles of bromine atoms, because that's what we're after, versus moles of CBr4, the whole enchilada, the whole molecule. So we have 4 moles of Br for every 1 mole of CBr4. All right, and we're going to use that as a conversion factor. I'll show you where that fits in. So the problem starts out just the same way as we were trying to get to the moles of CBr4 molecules. In order to do that, we're going to need to convert grams to moles using the molar mass of CBr4. Sometimes students don't believe me that I have to see this step on your work when you work it out. It's so tempting just to stick it in your calculator. And there are some like very slick little programs out there that, apps even, that you can type in the formula and it will calculate a molar mass. It's like, how fun is that? Pretty fun, actually. There are some apps. I'll see what I can find online, and they're calculators. So anyway, that's the molar mass of CBr4. So it looks like this then. It starts out the same as before. So we're going to start with the mass of the compound, 1.92 grams of CBr4 over 1. Then we're going to use that molar mass. Oh, that's pretty heavy, isn't it? We want grams to cancel, so we're going to be using what I call the flipped version of the molar mass. 1 mole of CBr4 over 331.6 grams. 331.61 grams of CBr4. Grams cancel. Now, here's where it diverges. We would be done if we were after moles of compound, but we're after moles of bromine atoms. So what goes that last term? Anybody?
What are you saying?
So I want to be left with moles of Br, and I want moles of CBr4 to cancel.
So you go 4 moles of CB, or 4 moles of Br over 1 mole.
Yeah, that's exactly it. We go 4 moles of bromine atoms, 4 moles of Br over 1 mole of CBr4. That's it. And do you guys buy that 4 and that 1 are exact? Okay. So we need to round according to significant figures. How many sig figs?
3.
I'm liking it. So this is what I got. 0.0232, and units would be mole Br. What do you think? That's it. Okay, so I think we're ready for an assignment slide. Arr. And these are all due, none of these to take out. Let's see if I can pull these up.
Do you offer extra credit in your?
No, not really. It's okay to ask, but no. So we'll take a look at these. These are 3-4 problems, and each of them have multiple components to them. So good thing that you guys have till Wednesday to get all these done. No kidding. I'm just kind of kidding, kind of. So I have some hints that you may or may not need. For this one, what is the molecular mass of C5H11NO2S? Okay, I'm sure you guys can use the periodic table and knock that out. Okay, show all your work. And then for the next one, what's the number of what is the number of moles, now not hydrogen atoms, but the moles of hydrogen atoms per mole of the compound? Looks like 11 to me, right? 11 moles of hydrogen per 1 mole of the compound, per the formula. C, what's the number of grams of carbon found in 1 mole of the compound? Mm-hmm.
So for B, 11 moles of hydrogen would be the answer.
I think so.
Okay,
I wrote it as an equivalency statement, but
Yeah.
to me, 11 moles of hydrogen answers the question.
all right, cool.
Yep. For C, you're after grams of carbon in 1 mole of the compound. So to me, I would kind of maybe work this as a factor label. I would start with my first term, 1 mole, exactly 1 mole of the compound. I would use the molar mass of the compound. Actually, looks like what you, well, you're close when you did A, which is the molecular mass, but the molar mass is the same number, but change the units. And then, wait a minute. Oh, no, I'm doing this wrong. My hint is different than this. I said take mole of the starting with 1 mole of the compound. You have what, 5 moles of carbon per 1 mole of the compound? That would give you to 5 moles of carbon. And then I would simply use that 12.01, that decimal number for carbon, to knock out the mass of the carbon. That's even easier. Final answer. The last one, you're starting with a different term. You have, instead of 1 mole of the compound, you have 9.07 moles of the compound. And you're supposed to come up with the number of carbon atoms. So C and D kind of start out similar, okay? Where you go from moles of the compound to moles of carbon using the 5-to-1 ratio. And then here, you're not after mass, you're after number of carbon atoms. So this is another place where you guys get to make sure that you're on track with regard to it's atoms, not moles. So you're going to use Avogadro's number there. I'll just put all these up here. So we have 4 parts to this one. I'll push these out there as hints. Kind of some different nuances. Okay. Have 3 parts to question 11. 11C is kind of fun. And then your last one looks like this. So, again, I'll push these out as a PDF. Okay, because I want to get to this last type of problem. So, this last type of problem deals with salts. Do you guys remember over here we talked about pure substances or mixtures, and if it's a pure substance, it can be an element or compound. And there's 2 types of compounds. There's molecular compounds or ionic compounds. A lot of times ionic compounds, kind of a general term, is a lot of times they're just called salts. An ionic compound is a salt. If you've ever used a desiccant, how do I say? I think we'd be right. A desiccant is like those little packs that you put in your purses, or they put in purses so they dry your purse out or whatever. There are salts are notorious, are great at having an affinity for certain waters. So if you take an anhydrous something, okay, that wants to have waters of hydration, it's great at basically drying things. It makes a great desiccant. So hydrated salt, the hydrated salt will be the natural form of the salt, given kind of its ways. But we can drive off those waters of hydration with heating. Okay, so we're going to work some problems like that. So when you have waters of hydration, it looks like this. You say dot. So this would be barium chloride, or BaCl2 dot 2H2O. So the compound is barium chloride, but for every 1 barium chloride unit, you have 2 H2O units, 2 waters of hydration. And it's kind of a crystalline lattice electropotential metric sort of thing, I think. So there are a couple of other salts I've got here. Copper 2 sulfate pentahydrate. Now we'll be talking about naming compounds. I can tell you right off the bat that we aren't going to be dealing with molecular compounds, so you guys aren't going to be using the penta prefix. Penta, of course, means 5. Okay, but copper 2 pentahydrate. Okay, CuSO4 dot 5H2O. And
Now the I and the 8, is that usually, 8 is usually associated with like 3 or 4, and then I is 2.
now that we will be talking about when we talk about, we will name ionic compounds, and I think this might be what you're saying. The 8 usually, and I always think is I ate too much oxygen. So 8 always means relative to that element, you have more oxygen. So kind of the opposite of sulfate would be sulfite. And as it turns out, sulfate is SO4 2 minus, and sulfite, as some of you might know, is SO3 2 minus. So the 8 has a little more oxygen. And then, of course, we kind of had something going down here with nitrate and nitrate. So I did go ahead, and these are, I got these off the internet. You guys don't have this slide. But I just kind of wanted to see, for instance, the barium chloride dihydrate. You know, there you go. There's your barium chloride, 2 waters of hydration.
So are those hydrogen bonds in the chlorine, or does it just kind of line up that way?
So these are, let's see if I can do it. These are, I usually use a dash, dash, dash. These are ionic bonds, and they're not shown here, and I'll change my color. There would be, and I don't know how it goes, but these waters of hydration, those bonds must be weaker because we can zap that with some thermal energy and break those bonds of hydration.
So those
What?
are hydrogen bonds?
No,
Or
they're not hydrogen
they're
bonds.
not
No,
hydrogen bonds,
no.
okay.
Hydrogen bonds are reserved for, they're not hydrogen bonds. Yep. And then this is the copper 2 sulfate with the 5 waters of hydration. I thought this was kind of cool, how they kind of circle around like that, the circling the wagons. And this is the iron, was it iron 2 nitrate with 9 waters of hydration. That's kind of cool. Kind of pretty. Okay, so let's work a problem, a hydrated salt problem, and we'll see how it kind of fits in with what we've been talking about. So I actually made like a little animation to show you this problem. So this is a hydrated salt problem. We're dealing with a copper 2 sulfate, but notice this little X here, copper 2 sulfate. We don't know how many waters of hydration are with each copper 2 sulfate salt formula unit. We don't know. X is our variable we're trying to find in this particular problem. Okay, notice they give us a couple of weights, and this is where I'm going to kind of show you the problem. They give us the weight of the hydrated salt, which is the bigger one. They zap it with thermal energy, and then they give us the weight of the dried stuff, the copper 2 sulfate. So, of course, by difference then, we can go ahead and get the mass of the water that must have been driven off. Uh,
0.369.
right. I knew I made one. I must have put it here. I need to combine these two. You got it. So here's my little picture. If I was working this problem, I would draw a picture because it buys me time. I like pictures. So those little specks there are my water molecules that are going to be driven off. Notice I have or I will have the mass written underneath it. Okay. Like you said, we can get the mass simply by difference, and that's what we're going to do here in a minute. But I want to show you how we're going to work this problem. So bottom line, I'm sure you guys buy, we can get the mass of the water driven off. We were given the mass of, we call this the anhydrous salt, copper 2 sulfate. So we can actually then use the molar mass of CuSO4 to get to moles of CuSO4. We can use the molar mass of H2O to get to moles of H2O. Then, if we have those two relative moles, we're almost done with the problem. So when we work this problem, we're simply going to put the moles of waters of hydration, divided by the moles of the formula units, the CuSO4, and that ratio actually should be close to an integer, hopefully. And that ratio actually is going to be our X, our waters of hydration. Okay, so here we go.
What's the dot mean again?
The dot, what does the dot mean? It means that it's a hydrated salt.
Okay.
Yep. Dot X, which we don't know how many waters of hydration there are per formula unit of CuSO4. So in that sort of scenario, we need the molar mass of copper 2 sulfate. So we'll take 1 times 63.55 plus 1 times 32.07 plus 4 times 16.00. So our molar mass that we use for copper 2 sulfate is 159.62 grams per mole. Chemistry problems are notorious for you kind of work it in pieces and then you kind of...
Give me 1 second with that, please.
Okay, I'm going to go on to the next one though. And the next one, the molar mass of water, you might be knocking this out a lot in this class. We do a lot with water in chemistry. Molar mass of water, we need to take 2 times the decimal number for hydrogen, 2 times 1.008, plus 1 times 16.00. So that equals, rounded to 2 decimals, 18.02 grams per mole. That's the molar mass for water. So I'll ask a rhetorical question. Do I need to see this on your work? Yeah. You need to go ahead and knock this out. And labeling them is nice too. So, okay. So, we'll go ahead and, like I think Joshua up here said, we can get to the mass of the water driven off by simply taking the mass of the hydrated salt, that 1.023 grams, and from that subtracting 0.654 grams. That was the mass of our anhydrous salt. So we must have driven off 0.369 grams of water. So we're ready to cut to the moles of water and moles of copper 2 sulfate. So the moles of water will simply be that mass of water we came up with, 0.369 grams over 1. And we want grams to cancel, be left with moles, so we're going to use what? The flipped version of the molar mass. So we'll put, for water, 1 mole over 18.02 grams. So our grams cancel, we're left with moles. Now notice that since I'm labeling my step, moles of water, I don't have to put grams H2O, mole H2O, grams H2O. If I weren't labeling it like that, to me, I think I would have to be more explicit. Because otherwise you're going to have two grams to moles problems, okay? And you'll get confused. Or I'll get confused when I go to grade it. So rounded to 3 significant figures, we have 0.0205 moles of H2O. 0.0205 moles. And we're going to do a similar thing to get to the moles of copper 2 sulfate. Given in the problem, the anhydrous salt was 0.654 grams over 1. The molar mass we knocked out for CuSO4 on the previous slide was 159.62 grams per mole. But we need the flipped version of it because we need grams to cancel, be left with units of moles. I'm like in 3 sig figs again. 3 significant figures. I got 2 leading zeros and a trailing 0 after the decimal. So 3 sig figs, 0.00410. So what was the last step, did I say? I think. What's that?
You subtract from the ratio?
The ratio? Ratio of what? Yep. We're almost there. We're just going to get the moles of water to moles of CuSO4. That's the last step. So we put that 0.205 moles. No, darn it, did I say it wrong? We put that 0.0205 moles of H2O over 0.00410 moles of CuSO4. And hopefully it's about an integer. If you don't get an integer, I've done something wrong. And this one ends up being, with 3 sig figs, 5. Okay, so 5.00 units would be moles of H2O per mole of CuSO4. And that's our X. That is totally our X. And that was the point of this exercise, to use the mass of the hydrated salt, mass of the dried salt or anhydrous salt, to actually deduce the waters of hydration. So the formula for this hydrated salt is CuSO4 dot 5 H2O. Which wasn't that one of the 3 salts copper 2 sulfate. You're like, well, you already told me it was 5 pentohydrate. Well, now we know it, for real. Okay, so if you would, please mark a line through problem 73. 373 is, will be assigned later, if I remember. But you've got enough information. The 22, 71, and 74 are hydrated salt problems. So I'm going to just kind of show you right quick, and again, I'll push this out there. Kind of a long story, but this one, it's not animated. Here it is. Okay. So this one looks like this, 3 problems. This one is different, isn't it? Welcome to chemistry problems. We're given the waters of hydration, and we need to come up with the mass percent of water. And I kind of tell you in my hints how I would do it. Now, these problems, again, a lot of times students do it different ways than I do. But what I would do is come up with, for one repeating unit, what is the mass of water in one repeating unit of CR quantity NO3 3.9H2O divided by the total mass of the hydrated salt. That's what I would do. The next one looks like this. And again, at the picture, don't read the word, just look at the picture. So in this case, you don't have a mass here, but you have a mass of water driven off. Okay, and you're supposed to come up with what is the mass of anhydrous. Oh, yeah. Check it out. We're not drying it. We're hydrating it. Okay? So we're taking the anhydrous stuff, adding water to it, and getting the pentahydrate, that copper 2 sulfate pentahydrate. So basically, they want to know what is the minimum amount of this you need to start with in order to add that much water to it. And then the last one looks like this. This one is very similar to class, isn't it? Where we have the hydrated salt over here, we have the anhydrous salt here, and you're supposed to come up with the waters of hydration. This is very similar to what we did. You're like, can't you just have one sort of problem in chemistry? No. Okay. So that's it. Have a great weekend. I'll see you Wednesday. I will be in my office, so if you have any questions on Monday, definitely stop in. I'll probably be bored. I'll get out.